Before I start, I would like to say that I'm really excited to present at the first edition of the NorthSec conference, and it's a big pleasure for me to be on this stage among the other speakers. So today I will be speaking about practical approaches to reversing object-oriented malware using your HexRays decompiler, which is a part of the IDA Pro disassembler, and this project has been done together with Aleksandr Matrosov, who is not here, so I'll be presenting on my own today. So let's start first with the brief overview of today's presentation. So this is going to be a practical presentation, and just to define the scope of the talk, we will limit our attention to C++ as a object-oriented language, because this one is the language which causes a lot of pain for reversers. We will also limit our attention to a specific compiler, Microsoft Visual C++, to produce to compile the code here, because some of the approaches here I will be presenting today and speaking about, they may not work, for instance, for GCC Linux compiler. And we will use all the examples will be based on the IDA Pro and HexRays decompiler, because this is a very versatile tool and is their de facto standard in the industry. So we will have three parts in this presentation. First, we'll be speaking about why is reversing C++ malware is difficult, how it is different to say lots of malware written in C. We'll just take some simple examples to understand what's the difference, and then we'll move toward malware seen in the wild and see some use cases or what are the problems with reversing this malware, and how to approach this problem. And finally, in the third part of the presentation, I'll be speaking about how to automate some reversers tasks using HexRays decompiler. So just to introduce the context, I want to bring your attention to this slide. This slide shows your modern C++ malware used for targeted attacks. So the list is not exhaustive and complete. It's not the goal. It's just to highlight the importance of the dealing with the C++ code, because all this malware is developed using complex frameworks, and it is challenging for reversers, for malware analysts to reverse this malware, to understand its functionality, what is it doing. So we can see a few nice examples, like in 2010 Stuxnet, which challenged the industry, malware targeting Iranian nuclear facilities. Then in 2012 we discovered a Flamer. This is another malware, non-arguably one of the most complex to analyze, and recent examples with their animal farms and SandNet. So everything is in C++ with the complex framework. So let's move on and speak about why reversing C++ code is a hard problem. Why is it different compared to the other C languages? So please take a look at this slide here. And let's compare two snippets of the code, one on the left-hand side and the one on the right-hand side. So on the left-hand side, we have a very simple code. We have a class cat with here one method eat, and we have just one instance of this class over here. We'll use mouse to show you over there. We're calling eat method. So everything should be clear here. And on the right-hand side, we have a little bit more different situation, because we have a basic class animal, and the cat is actually a child class, so it's inheriting from animal, and we have a virtual method it. So the principal difference here, we don't have any virtual methods on the left-hand side, but we have virtual method here. So let's compare the code which is produced by the compiler to see how this is here different. So I hope you can see this screenshot from the HexRays compiler. We have an allocation memory for the object. We have initialization of the object here, where the constructor is called, and we have an execution of the method eat. So everything here is pretty straightforward and nothing special like as if we were reversing C program. But with virtual method, the things are a little bit different, because now we have a call to our method eat, but it is not called directly. A pointer to this method is stored in some variable, which is known as a virtual function pointer table. And this is the key difference, because the method is not called directly, but it is called using a pointer which is stored in some table. And where this table is initialized, this table is initialized in the constructor at the creation of the object. Why does this happen? This happens because this method is virtual, and at the time of the compilation, generally at the time of the compilation, compiler doesn't know which method exactly which is going to be executed. If it's going to execute method which is implemented in the class cat, or potentially there may be some other derived class with the base class animal, which will have the other implementation of the eat method. So it encodes this information at the time of the creating the object, and then it uses this table of the virtual functions to execute this call. And let's speak about virtual functions table. As we have seen on the previous slide, we have an instance of the type A, class A, and we have a virtual function table. So this is a table which lists pointers to the methods corresponding to this class. This is this rectangle in the middle. And additionally, we may have some additional information which is called RTTI object locator. RTTI stands for runtime type information, and this is your optional object which may be inserted by the compilers. So compiler inserts this object when you're using dynamic cast or type ID information, because in this case, during the execution of the program, the runtime environment would need to know information about the types. So this information is stored in the binary as well. And just to show you the example, so we have here a constructor. I hope you can see it well. So this is where the virtual function is virtual table is instantiated. This is the pointer to this is the layout of the virtual table. We can see here pointers to the methods actually over here. And this is information about the RTTI object information. So what's the problem with the virtual functions? First, it leads to indirect method calls, which is difficult to analyze in the static context. Because when you're looking at the program statically and you encounter at some point a call to the virtual method, it is not clear exactly where the control is going to be transferred to. And to be able to identify this, you would need to track back objects to its creation to find constructors to the particular place where this object is instantiated, and from the constructor you just go and grab the pointer to the virtual table, which is also generally a hard task. Because, for instance, you are maybe reversing some instance of the code which reads objects from the vector and executes some routine in the virtual table, but where these objects came from is not clear. Another problem with the C++ reversing is using C++ templates. This is another way to implement polymorphic types. For instance, as we can see here, we have different vectors of integers, strings, characters, or some custom type. And every time when you use this here, these types, the code will be unwinded by the compiler and inserted in the binary. So we'll produce a lot of extra code to analyze. This is the first problem. And the second thing, when you're using C++ templates, it creates some problem with the identifying some standard library code. For instance, IDAPRO has a special tool, which is abbreviation FLIRT. It can highlight, as shown here, the standard library code, so you don't have to reverse it. You just know that this is code like memory location, operator new, or some other. When you're using these templates, you can, the code is generated, the code is not pre-generated because library code is your coder pre-generated and you're just using this library to link it. So you can just put some signature on these functions and then you can easily retrieve them. In case of your templates, you are going to regenerate this code. For instance, if you are using a vector, the vector is defined in the header file. And as a result, the code responsible for handling methods of the vector will be compiled with your application, and you can play with different compiler optimization options to produce different code with the same class. And just to summarize some problems with the reverse in C++, so generally we have two problems. First, to reconstruct the type. When we have a constructor, first we need to find the place where the classes are instantiated. We need to reconstruct its attributes. We need to find virtual tables. And if we have information about RTTI in the binary, it is always useful to reconstruct class hierarchy, like which interfaces and which classes this particular instance which we are analyzing is inheriting from. So this is the first part. Let's now take a look at some real malware which we've come across during working on the malware analysis. And the first, I'm going to speak about the Flamer. Flamer is non-arguably one of the most difficult malware to analyze. One of the samples which we received is about 6 megabytes, which is statically linked with the Lua interpreter, SQLite database, and a lot of additional code to analyze. First, let's take a look at its framework, because it's very common for such complex malware to implement itself as a framework. And here, for instance, here we can see at the right in the center, there is a vector of tasks. So the tasks are some routines which are executed in the separate threads. There are different kind of tasks here. For instance, there is a task Merc, which is implements a fake Windows Update server to distribute malware within the organization. It just emulates Windows Update server, and when the computer operating system Windows requests for an update, malware sends its binaries with the as an update. So the computer installs this and it's running, and it used a forged certificate to be able to bypass authentication. The file finder is responsible for finding files on the machine according to some pattern. There are some. There is a task, for instance, idler, which is responsible for executing some tasks periodically. All these names which we retrieved from the binary, from the configuration information. So we didn't have any RTTI information in the binary, but in the configuration, maybe for debugging purposes or for communication with CNC server, they kept these names. So this is how we got them. So either has some other tasks which are executed periodically. For instance, this Beetlejuice is using Bluetooth facilities, Bluetooth hardware installed on the computers to be aware of the different instances which are infected in the networks which are air gap separated, which don't have, which are not in the same network segment. There is a frog module which is responsible for replicating itself using creating user accounts. IFRE is for distribution using removable media using Linka files. There is a vector of consumers. These are a kind of triggers. They are called in the Flamer consumers, and they are triggered when some specific event is happening. For instance, mobile consumer is triggered when a mobile device is attached to the infected computer. Media is when some media is inserted in the computer, etc. And there is a vector of the command executors. So those modules are basically responsible for dispatching commands from the command and control center. So let's speak about some types which we were analyzing while we were working on this malware. A lot of work was done with the standard types like smart pointers, string, vectors to maintain objects, or some other custom data types. Maybe these types are taken from some standard libraries. We were not able to identify these because we came across from different libraries, and it is very likely that this is some custom implementations of the types. And since they are used very heavily, they obstructed analysis significantly. For instance, smart pointers. I think for those who are not aware of what the smart pointers are, these are the objects which are help to manage pointers in C++ to avoid memory leakage. So they contain two fields here. One is the pointer to the object, and the second is the number of references. So it keeps track of the references, and when the number of references is 0, you can dispose the object and release the resources. And this is just an example of how a constructor of the smart pointer looks like. We are just allocating memory for a reference and initializing it with the object over here. Another type which is heavily used in this kind of malware is the vectors. This implementation of the vectors is definitely something different to, for instance, a standard template library vector implementation. The vectors are used for handling objects like tasks and triggers. It is very common, instead of just creating a thread in the computer, on the machine, the malware just creates a special object thread, inserts it into a vector, then passes this vector to the executor, which is just going through the elements of the vector and executes them. And those parts are implemented in different parts of the binary, so it's not clear exactly when you have a vector what kind of objects are in. And since this is implemented using templates, you don't have, you cannot recognize them automatically that this is your standard code. And of course, strings. Strings are used very heavily for paths, and a lot of work was done, maybe about 70% of all the code which is reversed. It is these vectors and strings and smart pointers. Okay, so now let's speak about how we're going, what are the approaches here, what is the methodology toward reversing object-oriented malware, and specifically C++. And here I want to bring your attention that when working with the object-oriented malware, we are shifting focus to type reconstruction, because when you're working with the C code, this is mostly all about reconstructing control flow graph. You need to understand where this function is called from, where it transfers control to, and what API routine it is using just to grab the context and describe this functionality. In C++, the things are a little different, because there is a lot of work between types. So instead of reconstructing control flow graph, we would need to concentrate on what types are implemented in the binary and how they are interconnected with each other. So to achieve this, we need to first identify object constructors to see where the objects are created to grab information about virtual functions, etc. We need to reconstruct objects and reconstruct their methods to see, to understand this functionality. So about constructors, sometimes it's tricky, but generally you can recognize constructor using some clear pattern. For instance, there is a memory location using new operator, and then the pointer is passed, as shown on this slide, to some routine over here, like we're allocating memory, and then passing this to this routine, which are inside does initialization and you're assigning a virtual table. Okay, so when we have identified constructors, we are going to reconstruct object attributes. We can efficiently use a SEER structure representation to describe the objects. And in the IDA Pro, we can use their IDA local types to create the structures describing the objects. Like here, for instance, this is one of the structure description of the object in the Flamer. When it comes to virtual functions, as we can see on this slide, we have a virtual function for a C-socket object. We can create the C structure to describe it in IDA Pro, here where the fields are the name of the methods actually. And we can then modify a pointer in the very beginning of the structure, which is struct C-socket, to point to this table. And when we will be decompiling the code, we will have this nice picture because it's very clear and straightforward. We have a structure, we have a vtable, and we have an execution of this routine, which we named. And this is readable code. Without this, we would just have some calls going to arbitrary, at some arbitrary offsets. So this is about Flamer. The other malware, which we will consider, is one of the modules of the operation send-need. We'll specifically restrict our attention to one of the modules, which is X-Agent, and tomorrow my colleague Jean Calvier will be speaking about this operation in details, cover all the modules. So let's take a look at the X-Agent framework. It is a little less complicated as the framework of the Flamer. We can see here that, however, it has a lot of similarities. For instance, we have a vector consisting of the objects which implement iAgent module. So these are the modules which are executed by the malware and kind of stand alone and communicating with the CNC server. And by the way, one thing to mention here that this modular framework is being used here in such a way that for malware developers, it is very easy to develop malware which is operating on the multiple platforms. For instance, we have modules which have with the same framework, but they are compiled for Linux and for Mac operating system. But the interfaces and the modules are the same. So we have here an agent kernel, which provides some basic services as local storage, crypter, and some reserved APIs and channel controller. Channel controller is a kind of multiplexer. It multiplexes your messages between channels, and the channel is the object used to communicate with your CNC server. In this case, we can see that there is one channel here, WinHTTP, which implements communication with CNC server over HTTP protocol. We have some modules here, module file system. This is responsible for triggering events related to our file system to scan for the files. Remote keylogger, as you can guess from the name, is just your keylogs the functionality. The process retranslator is a remote shell. Here is the architecture of the agent modules reconstructed. So all these modules implement a single interface, which is their iAgent module, consisting of 5 routines here. The first 2 are used to exchange information with CNC server, receive message from the CNC server, receive some commands and send message to or report something to CNC server. And there are some routines, get module ID and set module ID. Each module has its personal identifier, and the final is the method is execute module, actually run its functionality. Okay, how did we get all these names here on this slide? Thanks to RTTI, because in the samples we analyzed the contained RTTI information. This allows us to recover type names, reconstruct class hierarchy, and identify object virtual function tables. Like here is the screenshot from the plugin class informer, which automatically goes through the binary and extracting all the RTTI information. And we can see, for instance, here that the agent kernel is the implements two interfaces, iAgent module and iKernel provider. So this information is very useful for reversers. This is the good thing. The bad thing is that RTTI is not always available in the binary, and it is very compiler specific. For instance, RTTI information is not present for classes which doesn't have any virtual method, because in this case, your compiler knows at the compilation time what's the type of this class, and there is no need to insert RTTI in the binary. And this is, for instance, a screenshot, right, of the modular remote keylogger virtual table reconstructed using this RTTI plugin. Let's take a look at some of the modules here implemented here. So local data storage, it inherits, as we can see here, it implements two interfaces, iLocal parameter storage and iLocal data storage. Parameter storage is actually a registry reader-writer over here, so it can read and write data in the registry, and the file reader-writer does the same thing, but only with the files on the hard drive. The cryptor interface is used to encrypt messages in communication with CNC server. It has only three methods: validate buffer, encrypt buffer, and decrypt buffer. The cryptor interface is based on the RC4 implementation, and one particularity which I want to bring your attention here is that to encrypt a message, it uses a key which is hard-coded in the binary, but it also generates a random salt of 4 bytes. And when it encrypts a message, it generates random 4 bytes, concatenates with the key, and uses this information to encrypt the message. And then it appends this salt to the end of the message. So every time the same message is encrypted with the same key, the ciphertext is going to be different. And there are some other resort APIs. We have only here like APIs listed at the bottom of the slide: get volume serial number, create mutex, and shell execute. We also saw some types, heavily strings and containers, but in this case it was fairly easy to identify that this is standard template library classes. Over here, for instance, we can find the strings in the binary, and this is on the right-hand side we can see source code from the header files. So basically you're using strings and vectors from the standard library, which made the analysis significantly easier, because we know exactly what kind of types are used, and there is no need to reverse them from scratch. Okay, so now let's move on to the third part of this presentation and speak about how can we automate some tasks of reversing C++ applications, C++ or malware. We'll be speaking about a tool which is a plugin for the Hexrays decompiler. This is an open source tool which was first presented at RECon 2013. It was inspired on the work on the GABS bootkit when we were dealing with the position-independent code, and this is the first time when we conceived this tool. But later we decided there's some functionality which was suitable for working with the position-independent code actually may be applied to the object-oriented reversing. So before we speak about functionality, we need to introduce some basic things about HexRay's SDK, how it works. So because this is the plugin for the HexRays SDK, and to represent a decompiled function, HexRays uses a special tree structure which is called C-tree. Basically, this is a syntax tree structure which consists of objects which is of nodes which are called C-item T. There are 9 maturity levels because this structure is generated using several iterations, and you can actually hook at any level, but we are using maturity level final when this structure is ready to use. And on this slide, we can just see how, for instance, these expressions, this expression, variable 3 equals variable 2 plus variable 7 is represented over here. This is the variable 3, and this is the operator of the assignment. So assignment here, on the left-hand side, we have variable 3 over there, and on the right-hand side of the assignment, we have node add with the variable 2 and variable 7. This is the underlying structure. And these nodes, C-item, may be of 2 types, expression or statement. The statement is there maybe block, which is here in the curly brackets, or if, for, while. Expressions is everything what has type. You can do whatever you want with the C-tree structure, but you have to make sure that the type information is consistent, as shown here. Like if you're just doing assign into integer, you have to assign similar type. Well, in this case, it's the word, but that's okay, because the word and integer they have the same properties here, and the word is obtained as a result of the call to this routine, and this is the signature of this routine. So it returns the word and takes 2 parameters, the word and byte. We can see the word here, and the other parameter, third, is just here stripped. It's not on the screenshot. So you can do any manipulations with these nodes, and you have to make sure that the type information is consistent. Why we have chosen HexRays decompiler? Because this is assembler independent. HexRays supports x86, x64, ARM, so you don't have to care about specific compiler. You're just working with this C-tree structure, and a lot of work to construct it is handled automatically by HexRays. So we are just using this C-tree representation to work with this, and it offers also some classes to do traversal, like C-tree and C-tree parentity. There should be some demonstration, but I think I'm going to skip it because we're just running out of time. And this is I have 2 presentations, so I'll just spend a little more time on the second presentation because this one is more important. So how we are using this C-tree and how it is useful in the reversing object-oriented malware. We can reconstruct type using this representation. So for instance, on input, we can take a pointer to the object instance and its constructor, and then on the output, we can get a representation of this object. As shown here, for instance, to be able to reconstruct, we need to pay attention to some specific nodes of the C-tree. These nodes are memptr, IDX, memReference, call, ptr, and assignment. For instance, memptr is a dereferencing pointer within the structured specific offset. IDX is actually using an index to address specific element in the array. Memref is a reference to a memory, and so on. So for instance, we can see here over here on the left-hand slide that there is a reference to this field, virtual function table, and we can reconstruct this reference using this C-tray representation. So we are just monitoring MPTR. We are tracking this this keyword, and we see that at offset 0, there is a dereferencing of this pointer, so there is a field within this object, and we can build structure this way. This is here another example, but with here using PTR and assignment. We can see here that we have this code over there, which is the this plus 212, and this is an assignment operator. And we can detect that there is some field from offset 212 from the beginning of the object. So we are just creating some type. Since we know that the type of the assignment is integer, we're supposing that there is a 4 fields, 4 bytes at offset 212. And as a result, we can reconstruct the structure like shown here automatically, which is there saves here a lot of time in the reversing. For instance, here we have another example. We have this in the decompiler output, A1 plus 12. So we are just casting it to the pointer to this word. Then we are dereferencing the pointer and assigning some value over here. This is represented in the C structure like this. And we can understand that at the offset of 12, there is some member which receives this value. And this is how we have this structure signature. So over the last few weeks, we have been working on the special edition of the HexraysCodeXplorer for the NorthSec conference. And in this special edition, we implemented automatic virtual table identification and type reconstruction. So basically, we are scanning the binary for virtual tables in it. So we know where the virtual table starts, where it ends, and we can create structure describing this virtual table. And once we are reconstructing objects, we can create an automatically generated type here. For instance, this is the type for local data storage, and it has 2 virtual tables over here, this one and this one. We automatically generate these structures for this table and show them at these parts. And these are the tables which are located within the binary. And there, this version supports IDA Pro 64-bit as well. So I have some demonstration to show you how it works in action. We will use okay, you can see it over here. Oops. So this is a module of the X agent. Let's go to this routine. Yeah, I'm just trying to play something with the resolution of the screen to make sure. So this is the one, and okay, let's try. Okay, I think this is better, or yeah, so we're just going here. This is the routine of the X agent module. So I'll just committed some fields here. For instance, we can go to the constructor of the agent kernel, which looks like this. This is a pointer to the instance of the object passed as a parameter in the register ECX, and this is how the fields are initialized. So let's reconstruct the object like this here. So we need to enter name of the type. We are entering agent kernel. And we have automatically reconstructed fields over here, and we have created structures for virtual tables. So open subviews and go into our local types here. We can go down and see this one is here, and this is it. We can go down and reconstruct the other one. Channel controller, for instance. Let's go here. We can see the same constructor. We're reconstructing type and entering channel controller. Again, this type is reconstructed, so we are just exiting from here, and we can see that this variable is then assigned to this one. So I need to cast it to the structure agent controller, which we created. Oops. Okay. This is it, and then go back to their channel controller, and we can see that this is stored in the field there, and this field. So this is type agent controller. We can rename it as the channel controller. And the most important thing is we need to reconstruct it your type as well. So we're channel controller. Okay, and now when we are going this variable, we can go to this method, which is to register channel. This is another object which is created. So we're just going to go here and see that this is the pointer to the agent controller which we just reconstructed. We need to cast a type. Struct agent controller. And see here if it is being used. Okay, I think we can see it here. Now we have this automatically reconstructed at this point, and we can use this method is executed, so we can just navigate into it, and this is it. This is how it works, because otherwise you would have this call, which is rather meaningless. You don't know what is here at this offset without reconstructing this type. So yeah, this is about the this is about the demonstration. Okay, let's go on. And just to wrap up the presentation, I would like to say a few words about the next plans for the project. So we are just going to use we are going to switch to IDE Python, because right now the plugin is developed in C++, and when we started to work on the plugin, there was no IDE, there was no Python interface. So we did everything in C++. But why Python? Because its interface now is more consistent. When a new version of the IDE or IDE SDK is released, the developers sometimes change something in the interface. So you have to, sometimes your code is not compilable because there are some changes in the SDK, and you need to see what are the changes and adjust your code. But with the Python, this is okay because the interface is pretty much consistent and it's not changing. It is the way easier to develop. For instance, this small plugin, which is just printing the types of the blocks in the C tree structure, looks very nice and very neat and very small. In C++, you would have got something bigger. And some plans about further research and development. So something that we would like to improve. First, our version works for Visual C++ compiler. It would be interesting to see if it's working on GCC compiler samples and to port it to its support for GCC compiler. Another interesting thing is to find cross-references to the object attributes. For instance, when you have a type and there is some field in this type which is being used and referenced, you want to get the other methods which are modifying this field. And another interesting thing is to look at their code similarity based on data flow analysis. For instance, to find similar code based on their patterns of the access to these structured fields. For instance, sometimes existing tools there which allows you to assess how one code is similar to each other doesn't handle it very well because of their code is recompiled with different compiler options with some optimization. And sometimes these optimizations, they render code completely different. So inlining functions, omitting frame pointers, makes it difficult. But generally, the data access patterns should persist among these transformations. So this is an interesting field for the research. So for me, that's it for today. Thank you for your attention. And if there are any questions, I can take any.